This is a recording for Physics 1607, Fall 2013 at Auburn University. This is an example problem that I'm going to work from Chapter 4 of your textbook, Young and Friedman. This is problem 428. The situation is this. We are told that there are two blocks. There's block A and block B with masses m sub A and m sub B respectively. And that these two blocks are subject to an applied force, which I've labeled here as F, which is being applied to block B. And we're also told that between the surface that the system rests on and block B there's no friction, but that there is friction between block A and block B, just like I've labeled here. And that's actually a pretty crucial thing. This friction here is going to be pretty crucial, and I'll show you why in a second. So the problem actually asks us to assume that the system is in motion and that A and B stick together just like they are. They don't change their orientation to each other. And we're asked to draw a detailed free body diagram on block A while it's in motion. So I will do that in a second, but I want to start with drawing a free body diagram on block B. I think that'll be instructive, and we might get some information out of it that we'll need for block A. So I'm going to start this off just like normal with a dot. And I do that because as of now we don't care about where we apply the force on block B. We will eventually when we start talking about moments and things that cause rotations and torques and things like that. But for now, we're just worried about the translational motion of the system. So we're going to assume that whatever force we're applying is being applied at the center of gravity and that we don't have to worry about any sort of rotations. So I don't need to draw a crate or a box, I just need to draw a dot. So I'm going to do that. And now I'm just going to add the forces that are acting on block B. That's a very crucial distinction. We only want the forces that are acting on block B. It may well be that block B is acting through some forces on other parts of the system, but we don't care about that, at least for the free body diagram of B. All we care about are the forces that are acting on block B. So if you remember our two-finger rule from class, the first finger is gravity, which is pretty easy in any normal coordinate system that's going to be acting down. Of course, you're always free to change that, but I'm going to call that the weight, and most of you know that that's going to be calculated by the mass of block B times the acceleration due to gravity. And the other finger after gravity is whatever's touching it. So what's touching block B? Well, the first thing I see is the floor. So I'm going to have this, and most of you will recognize this as the normal force. It should be an N, not an M. As I said in class, I don't particularly like that designation because it doesn't give you a whole lot of information about what's providing that force. In this case, it's the floor. The floor is exerting the normal force onto B. Normal just means perpendicular or orthogonal. And of course, this force is perpendicularly applied from the surface. And so we have the normal force. What else is touching this thing? Well, the applied force is touching it. We don't know quite how it's touching it. It might be a cable or a string. Somebody might be pushing it. I mean, somebody might have hooked this thing up to a yoke of oxen. We don't know. We don't really care. We know that if there's some sort of applied force that's not gravity, something's touching it. Guaranteed, unless you're talking about electrostatic forces, which we're not. Right now, we're talking about mechanical forces. So, is that everything? Well, no. There's something else that's touching B. Notice block A is touching B. And it probably doesn't take a whole lot of imagination to see that the force that A is going to exert on B is going to be directed downward as well. And I'm going to call that F sub A. So don't let my subscripts confuse you. This is the block exerted by A. Sorry, this is the force exerted by A. This is not the force exerted on A. Block A is exerting a force on B. So I'm going to call that force F sub A. So A tells me where that force is coming from, not where it's going. And I'm going to draw that a little over to the left to avoid confusion. If you're not dealing with a magnetic stylus and an iPad, you can probably get that a little closer with a good pencil. But I'm going to draw it to the left for some clarity. And strictly speaking, this should be drawn attached to the dot. So that's block B. And before I draw the free body diagram for block A, I'm just going to apply Newton's second law to this one. And now clearly it's not it's not accelerating in the y direction. You know, we're told that this thing is going to, but we're not told. We can safely assume that this is sitting on the floor. So I'm not even going to bother with the y direction. I think you guys can probably see your way through that. But the interesting thing here is the x direction. Sum of the forces in the x direction equals mb times the acceleration in the x direction. And this term, this summation term, is non-zero. In the other dimension, in the y dimension, after you unpacked all that stuff, you would find that it summed up exactly to 0 because it's not accelerating. But here, you have one force, and we're told that it's non-zero. So there's no way that this left side is going to be 0. So if the left side is not 0, guess what? The right side is not 0 either. There is an acceleration in the x direction. Guaranteed. Okay, so let's move to block A and see what that stuff we just did tells us about block A. I'm going to draw a free body diagram, and same rules apply. Gravity's touching it. Gravity's not touching it. Gravity is the first finger. This is going to be the weight of block A. And block B is touching it. So this is going to be the force applied from block B to block A. So I'm going to draw it like that. If you don't like my subscripts, you are free to use your own as long as I understand and you understand what you're talking about. You have to understand because you have to solve the problem. I have to understand because I have to grade your problem. So it helps us both if you know what your subscripts mean. And so it looks like at this point that we're done on block A, right? We've got gravity and we've got whatever's touching it. Au contraire. The problem is, I'm going to break my own rule for free body diagrams, is that we're told that the system is moving together, and we found out from block B that the system is accelerating. When I said I'm going to break my rule, I'm going to put an acceleration on here. I'm going to erase it though, so it's okay. So I have an acceleration of block A in the x direction. And from Newton's second law, if I write down Newton's second law for this block, so I'm going to write it down here, sum of the forces in the x direction equals ma sub x. Let's make the distinction here. This is block A, and this is block B. But let's make the distinction. For block B, we looked at the system and figured out that the sum of the forces was not 0. Therefore, there has to be an acceleration. For block A, we're going to do the reverse. We're going to look at the system and say, you know what? We know from other parts of this problem that there's an acceleration here. So we are guaranteed that the left side of this equation is non-zero. There has to be a force there. And I'm going to erase this. So the question is, what is that force? And you need look no farther than the part of the problem which mentions that there is friction between these two blocks. There is going to be a frictional force acting in the x direction. It's that force that's going to provide your acceleration. So if you're wondering which direction does that frictional force act, you need look no farther than how block B, the direction block B is accelerating. And the way I've drawn it here, block B is going to accelerate to the right. Therefore, this frictional force has to act towards the right. It's the only force that's providing that acceleration. And some of you might be sitting there going, well, we've talked about frictional forces before, and I know that they always oppose the motion, so I don't see how that can be, because you're drawing the frictional force in the same direction as your acceleration, which is true. But notice, this is a static frictional force. Block A is not moving on block B. And if you ask yourself, if block B is going to move, which direction is it going to move? And if you think about that, you might finally come to the correct conclusion that if you're sitting on block B watching block A, and block A is going to move on you as you start to accelerate, you can probably come to the conclusion that you're going to see block A moving like this, right? Same thing when you put something in the bed of your pickup truck and you accelerate really fast and you hear it hit the tailgate, because from your perspective it's moving away from you. The same thing happens here. So the motion, if A were to move, would be in this direction, which is why the frictional force is going in the other direction. And that frictional force is exactly what causes block A to accelerate. Let's make that distinction really clear. The applied force F right here is what makes block B accelerate. The frictional force between block A and block B is what makes block A accelerate. You cannot say that this F makes A accelerate. It does not. It makes B accelerate. The frictional force makes A accelerate. That's a super critical distinction. Okay, good luck.